Okay.
Okay, very nice. So thank you, Gniewko. So actually, I borrowed the title from our last conference, I mean symposium on mathematical physics, which we had 2 weeks ago, which was quite successful. We had almost 50 speakers and more than 130 registered participants. And the symposium is very much related to journals which are edited by the members of our group in the center, Report on Mathematical Physics, which is now more than 50 years old journal, and Open Systems and Information Dynamics, which was established in the middle 90s last century. And people who are mainly involved in this business, Miłosz Michalski, Jacek Jurkowski, and myself. But of course, other people also help us, especially Gniewko, and Kasia Siudzińska. Okay, so this is a brief outline of my talk. So I will start with very basic introduction to quantum mechanics. Then I will talk about linear maps in matrix algebras, which are basic objects of our studies. And I will show you that these objects are very much related to quantum entanglement witnesses, and all this stuff. And then my plan is to talk about quantum evolution and completely positive maps. And finally, I would like to spend some time discussing the basic approach to characterize quantum evolution, especially quantum evolution beyond the unitary case. I mean, time local approach versus non-local memory kernels. But my idea is to give very basic talk, and so the idea is to try to find common language with other groups, especially mathematicians, and to find common interesting problems. So feel free to interrupt me whenever you want. This is just to try to find something in common problems, common interesting things. Okay, so let me start with a brief introduction to the notation I will use. So well, I will consider only finite in this talk, only finite dimensional Hilbert spaces. Okay, just okay, and I will use this notation for the inner product. And physicists usually assume that this inner product is linear in the second argument, right? So it is linear in phi, anti-linear in psi. Okay, L of H is for space of operators acting on H, of course, because H is finite dimensional, or all operators are bounded. Okay, so well, we can multiply in a standard way operators. That's why you may consider this as a unitary operator algebra, right? Okay, so in quantum theory, what are basic ingredients? So for any system, we assign a basically separable Hilbert space, but well, I will talk on about finite dimensional case. Okay, and well, states of a quantum system, so-called pure states, are represented by normalized vectors. Also, normalized vectors define a sphere, right? Well, actually, we have equivalence relation between any between vectors. This is a definition. So we consider two vectors as equivalent if they differ by a phase factor. And eventually we may define a true space of states of a system. Well, so this is nothing but projective Hilbert space. So this is a space of equivalence classes with respect to these relations. So basically you see that projective Hilbert space is nothing but the space of rank 1 projectors. I will use this very nice notation, which was devised by Dirac, well, roughly 100 years ago. Right? I hope it's clear. Right? This is rank 1 projector. So this is a projector projecting onto psi. Right? Okay, but we need a slightly more general concept of a state. And this more general concept we call a mixed state. So the mixed state is a convex combination of rank 1 projectors. Right, of course. Well, from the construction, you see that this is positive, semi-positive definite operator, right? Well, we call it density operator. Or after fixing a basis in the Hilbert space, we usually call it density matrix. So it's semi-positive definite and normalized. Well, trace is 1. So of course you see that the space of mixed states is a convex set, right? And this rank 1 projectors define set of rank 1 projectors. This set defines extremal points. Right, so any element, any density operator is a convex combination of extremal points, right? Okay. And the second piece, so these are states, right? So this is the representation of states. Well, and the second ingredient are observables, physical quantities. So any physical quantity is represented by, well, self-adjoint operator, right? And the crucial ingredient of the story is a mean value of well, so given a state, rho and physical quantity represented by self-adjoint operator, trace of rho A represents a mean value of this quantity in a state rho. So basically, this is a result of experiment. And we perform an experiment on a system. Well, our goal is to measure the observable A, which represents some physical quantity, and as a result of this measurement, one gets this value because rho and A are Hermitian, right? This result is real, right? Real number, result of the measurement. Okay, so we have two basic sets, right? Hermitian, semi-positive, normalized operators, and this represent quantum states. And on the other hand, we have Hermitian operators, which represent physical quantities. We call it observables, right? And we have this pairing, which defines the result of quantum measurement. Okay, very good. So now let's consider linear map, which maps some well, operators acting on H into operators acting on H prime. Right, so we have two algebras. Algebra of operators acting on H, algebra of operators acting on H prime. And we are looking for mapping operators from one algebra to operators from another algebra. And of particular interest are so-called positive maps. this is a definition, map phi is positive if it maps semi-positive element from this algebra into semi-positive element from the second one. Right, so this is a very simple definition. And another important property is trace preservation, which is obvious, right? Well, the map is trace preserving if it does preserve the trace, right? So the trace of phi of x is the same as trace of x. And it's a trivial observation that positive trace preserving maps, right? Such maps map density operator acting on H into density operator acting on H prime, right? So any positive trace preserving map allows to transform states, mixed states corresponding to Hilbert space H to mixed states corresponding to Hilbert space H prime, right? I hope it's this very clear concept. Okay, now look. So now suppose that I have two systems, quantum systems, S and S prime, and corresponding Hilbert spaces, H and H prime. Now I consider a system which is composed of these two, right? So I consider a composed system, S and S prime, right, as a single system. So S is just one subsystem of this entire system, and S prime is another subsystem. And quantum, one of the basic assumptions of quantum physics tell us that if we compose two systems, the corresponding Hilbert space corresponding to this composed system is nothing but the tensor product, right, of Hilbert spaces corresponding to original subsystems S and S prime. Okay, pretty simple. But now suppose that I have two positive maps, right? Phi and phi prime. So phi is a map acting on observables, sorry, on operators on the system of system S, right? And another map phi prime, which acts on operators of system S prime. Okay. And of course, it's very easy to define a tensor product of two maps, phi tensor phi prime. And of course, this resulting map maps operators of the composite system S to S prime into the same algebra, right? And now look, now the surprising fact comes out, namely, even if these two original maps, phi and phi prime, are positive, it may happen that the tensor product of these two positive maps, phi and phi prime, is not a positive map, right? So tensoring two maps which are positive, in general, gives a map which is no longer positive, right? So you may ask, what goes wrong? Right? Why is the tensor product of two positive maps is not positive? And actually, this is the reason is very, very interesting. Namely, it is very much related to a key notion of quantum physics, namely quantum entanglement. So now let me introduce a very important definition. Again, suppose I consider a composite system, right? Living in the tensor product of two Hilbert spaces H and H prime. I will call a vector psi from the tensor product to be separable, which means not entangled, right? Not entangled, we call it separable. It has nothing to do with separability of the Hilbert space. it might be a bit misleading for mathematicians, especially. So not entangled means that it can be represented as a just simple tensor, right? Tensor product of two vectors, one from H and another one from H prime. So this is a concept of separability for pure states, right? Vectors. And it can be nicely generalized for mixed states represented by density operator. As you see, a mixed state is separable, again, meaning not entangled, if and only if it can be represented as a convex combination of separable rank-bound projectors, right? So very, very simple definitions of separability for pure states and separability for mixed states. And look, if I take tensor product of two positive maps and apply to separable density operator, so it's very easy to find what the result is. Well, phi acts on this projector, phi k, and phi prime acts on the second one, right? Phi prime. But both phi and phi prime are positive maps. So phi acting on this projector gives positive operator. Phi prime acting on this gives again positive operator. So I have a tensor product of two positive operator, which is positive, and then take a convex combination of positive operators, which is by construction positive. So you see, whenever I apply tensor product of two positive maps to a separable state, I get a positive operator. So the reason why, in general, tensor product of two positive maps is not positive is just states which are not separable. So due to the existence of states which are not separable, we call them entangled. It may happen that if you apply tensor product of two positive maps to a state which is entangled, the result might be an operator which is not positive. So we see that we have quite nice relations between two very nice concepts. I mean, the concept of positivity of a map, right? And the concept of state which is separable, meaning not entangled. Okay. So to deal with composite systems, it's not enough to consider, as you see, positive maps, because positive maps do not behave well after tensoring, right? We need a much more refined version of positivity. And this was provided by Steinspring in 1955. He introduced a very nice concept, namely, suppose I have a map, again, linear map, acting between these two operator algebras. Now I call this map K positive if the following extended map. So I consider now K by K matrices with entries from this operator algebra, right, as inputs, and as an output state, K by K matrices with entries from this operator algebra, right? So I denote this extension like that. So identity, this is K-dimensional identity trivially acting on K by K complex matrices, right? So the map is K positive if this extended map is positive, right? And eventually, the map is completely positive if it is K positive for all possible K, right? Well, if K is 1, we just recover the definition of positivity. Okay. Now, 20 years later, after Steinspring, Choi made a very nice observation that this chain of maps, okay, positive maps, is saturated. Well, well, D is the dimension of H, D prime is dimension of H prime, D star is a minimum. Okay, so the map is completely positive if and only if it is D star positive, right? And we have the following chain of inclusions, right? Positive maps, 2 positive maps is a subset of positive maps, 3 positive maps is a subset of 2 positive maps, and so on. And eventually we have a smaller subset of completely positive maps. And now, okay, now let me give you an example. Very simple example. Again, this was provided by Choi in the 70s. So let me consider one parameter family of maps, phi A. A is the real parameter. And this is a definition, right? So phi A acting on X, this is a definition. So I take this parameter A, and this is identity operator, trace of X minus X. And it's not very difficult to prove that this map, phi A, is K positive, but not K plus 1 positive, if and only if the following condition is satisfied, right? So you know, controlling this parameter, we can control K positivity of this map, right? Okay. Very good. So once again, we have definition of K positive maps, and eventually definition of maps which are completely positive, which means K positive for arbitrary K. Okay. Now comes a very nice result, again proved by Choi, that the very notion of complete positivity is a spectral property. What I mean by that, suppose I have a linear map, right? And for this map, okay, now I fix a basis. I fix a well, orthonormal basis in the Hilbert space H, right? And these are basis vectors, right? I enumerated them from 1 to D, right? Okay, I defined this rank one operators, ij, right? Tensoring with phi acting on this rank one operators, and eventually I take a sum. We usually call this operator Choi operator or Choi matrix. And then comes a beautiful result that this map phi is completely positive if and only if the corresponding Choi operator is positive definite. But to be for an operator to be a positive definite, this is just a spectral property, right? You check for the spectrum. This is Hermitian, so you check for the spectrum. So whenever all eigenvalues are non-negative, you are sure that the original map is completely positive, right? So this notion, complete positivity, is a spectral property. However, beyond complete positivity, other notions of K positivity, they are not spectral. They are not spectral properties. Therefore, it makes the problem of constructing maps which are positive but not completely positive extremely hard. Okay. Now, having a linear map, any such map can be always represented in such a form. Well, the representation is not unique, but you can always find a family of operators AK, BK, and complex numbers CK, such that phi can be represented like this. Now, if the map is Hermicity preserving, which means that it maps Hermitian operators into Hermitian operators, you can always find representation of this form, where BK is the same as AK. Moreover, these numbers CK are real, right? So this is a representation of Hermicity preserving map. And eventually, if the map is completely positive, you can always find representation very similar to the previous one. But now, these numbers, CK, are not only real, but positive, right? Now look, because they are positive, I can rescale this operators A, I, like this. And eventually I have very, very simple representation. Usually it is called cross representation, but actually it was already found roughly 10 years before Krauss by Sedershan and collaborators. So we have extremely simple representation for maps which are completely positive. Now it turns out that completely positive maps play a key role in quantum physics, because any legitimate transformation on quantum system can be always represented by some completely positive map. I will show you more examples later on. Okay, and now if the map is not only completely positive, so it can be represented in this form, right? Cross representation, but it's also trace preserving, which means additional condition for this cross operators, Ki, right? So this is a condition for complete positivity. This is a condition for trace preservation. So any completely positive and trace preserving map is usually called the quantum channel. Moreover, if the following condition is satisfied, the map is not only trace preserving, but unital, which means that it maps identity in one algebra into identity in another algebra. And very often channels which are unital are called doubly stochastic, and actually this notion is very much related to stochastic matrices and doubly stochastic matrices. But I will not talk on this today. Okay, so Steinspring, who introduced this notion, already proposed very nice representations. We usually call it Steinspring representation or Steinspring dilation of completely positive trace preserving map. So any map like that can be represented as follows: that you can always find another Hilbert space, K, right? And an isometry V acting from H, the tensor product of H prime tensor K, such that the action of the map is defined as follows: that you take an operator X then you sandwich with V and V dagger, and eventually you trace out the degrees of freedom corresponding to the Hilbert space script K, right? So you trace out K. What comes out is a map which is by construction completely positive and trace preserving. Okay. So just to summarize, there is a crucial difference between positive, only positive, and completely positive maps. Namely, even if phi1 and phi2 are positive, the tensor product needs not be a positive. However, if you start with phi1 and phi2, which are not only positive, but completely positive, then you are safe in the sense that tensor product of two completely positive maps is always completely positive. This is a key difference. So the set of completely positive maps, which is again a convex cone, is closed with respect to tensoring. Okay, very good. So these maps are crucial for quantum physics if one would like to consider composite systems. As you already seen, in composing systems, in general, we have a problem with tensoring of positive maps due to quantum entangled states. Very good. Now let me present a key example of a map which is positive but not completely positive. So let me again fix an orthonormal basis in the original Hilbert space. Then instead of operators, we can talk about matrices. Okay, and let me consider a transposition acting on matrices. Right. Of course, it's trace preserving, because if I have a positive map, if I have a positive matrix after transposition does not change the spectrum. So the spectrum is the same, which means that transposition is a positive map. Of course, it's trace preserving because it does not change the spectrum. However, it is not completely positive. And look, I can very easily find an analog of Krauss representation. So let me introduce this 4 matrices: identity, and these 3 Hermitian matrices, F1, F2, F3. So every physicist loves these 3 matrices because these are famous for rescaled Pauli, so-called Pauli matrices. It's a simple exercise to check that the transposition can be represented in this form. So you see we have 1 minus sign here, right? Which proves that this map is not completely positive, because for complete positivity, you remember, we need Krauss representation. So all 4 pluses. Okay, so we have a very simple example of a map which is positive but not completely positive. Actually, this map is not even too positive. Okay. Well, let me illustrate this the action of the extended map. Okay, again in 2 dimensions. Right? So this is our original algebra we started with, right? So in 2 dimensions, transposition acts on 2 by 2 matrices, 2 by 2 matrices. So now I extend by identity operation acting on a set of 2 by 2 matrices, right? So I have a tensor product here, tensor product here. So eventually, this is a set of 4 by 4 complex matrices. The same is here. So now look, I take the following semi-positive operator. This is a spectrum, right? 2 and 000. and I perform transposition in every block, right? This operation is usually called a partial transposition, right? I do not perform transposition on the entire matrix, but I transpose each block separately. So these two blocks, this and that, are diagonal, so transposition does nothing, but transposition acts non-trivially on these two blocks, right? So I perform transposition here, I get this result, transposition on this block gives that block. And now you immediately see that the spectrum of this 4x4 matrix reads as follows. So you have one of eigenvalues strictly negative, which proves that this extended map is not positive, which means that the original one, which was transposition, is not completely positive. But of course, it's trace preserving, right? Because the trace of the original operator was 2, and trace of the final one is again 2. Very good. Okay, and now among positive maps, we have a very, very nice subset of maps which are called decomposable. So again, let me simplify the discussion and let me consider two matrix algebras. So I have as input, I take algebra of n by n complex matrices, and as an output, an algebra of m by m. I called positive map decomposable if and only if it can be represented like this. So I have two maps, phi1 and phi2, which are completely positive, but one of them I compose with transposition, right? Very simple concept. So because phi1 is completely positive, I have cross representation for phi1. I have similar cross representation for phi2 with operators bj, but I compose with transposition, right? So any map like that is by construction positive, right? And moreover, it is called decomposable. Very good. So I have a convex cone of positive maps, a convex subcone of positive decomposable maps, and finally, maps which are positive but do not belong to the subcone of decomposable maps are called indecomposables. Some people call them non-decomposable, right? And these maps are of particular importance for us. And the reason is again very much related to quantum entanglement. But before I show you the nice relation, let me quote the very beautiful result of Voronovich, who proves that if n and m, I mean the dimension of input and the dimension of output spaces, as follows, so 2, 2, 2, 3, or 3, 2. In these special cases, all positive maps are decomposable, right? And the first example of a map which is not decomposable was found again by Choi. So in his case, n and m are equal to 3, and this is a map, right? This is a map, so the map looks quite simple, but actually it's quite non-trivial to show that this is positive and not decomposable, right? So beyond this three special cases, there are maps which cannot be, there are positive maps which cannot be represented in this simple form. And these maps are very important for us, and actually in recent years, especially with Gniewko, but recently also with Anindita, who joined us last year. We did a lot of work related to constructions of maps which are positive but not decomposable. And with Gniewko, we have a topical review on this in Journal of Physics. But of course, any new idea is welcome. So why these maps are important? The reason is the same as I told you before. I mean quantum entangled states. So once again, this is a definition of separable states, pure and mixed. And actually, we have very nice results, which was proved by famous people from Gdańsk, Chruściński family. They prove that the state is separable if and only if the extended map acting on ρ is positive for any positive map acting from this algebra into that algebra, right? So whenever you have a positive map and you violate this positivity, you are sure that the state ρ is not separable, which means entangled. And now we have very important subclass of states. We call these states PPT, and the name comes from the following property. They are positive under partial transposition, right? Positive partially transposed. So I take a state. So I call a state PPT, positive partial transpose. If after performing partial transposition, we usually denote this operation by capital gamma, right? Which somehow represents partial transposition, right? We call a state PPT if and only if under partial transposition it is positive. So it's very easy to check that again, these PPT states are convex subset of all states. And of course, separable states, well, it's a simple exercise that separable states is a convex subset of PPT states, right? So we have the full set of states, right? Which is convex, convex subset of PPT and convex subset of separable, right? Of course, states which are not separable are entangled, right? And now we have a very nice relation between the concept of positive maps, which is decomposable, and the quantum state, which is PPT, positive under partial transposition. Namely, for any state which is PPT and any positive map which is decomposable, we have always positivity of extended map, right? So it proves that decomposable maps are useless if you would like to detect entanglement of PPT states, right? And in fact, we know that there are PPT states which are entangled. And to detect such states, we need maps which are positive and not decomposable. And again, using this result of Voronovich, which I already mentioned, you can prove that in all these three cases, right? Well, sorry. Voronovich proves that in all these three cases, all positive maps are decomposable, which means that in these three specific situations, all PPT states are separable, right? However, we know that beyond this three situations, there are PPT states which are entangled. Usually they are called bound entanglement, and there is very interesting physics behind this. However, it is very hard to construct such states. So any well, new idea is again welcome. Okay, so now let me pass to another very much related concept. This is a concept of so-called entanglement witness.
Okay, there is 48 minutes already.
Okay, so what should I do? So 10 minutes more, or I don't know. Niewko.
I think that we can proceed. 10 minutes more, it's, I
Sure,
think
sure.
people will survive.
That's
Okay, so we have another very important concept or problem we are working on. This is a concept of entanglement witness. So let me recall you. I have an operator acting on H, and I call, well, this operator is positive if and only if it enjoys this property for any vector psi from H. Now suppose that instead of single Hilbert space, I have a tensor product, H and H prime, and I have a linear operator, right? Now I call this operator block positive whenever this condition is satisfied. Of course, this block positivity is weaker property than positivity, because positivity requires positivity on all vectors, and now I require positivity only on simple tensors. Okay, and now if I fix an orthonormal basis in original Hilbert space H, I can again define this operator. Previously it was denoted by C phi. Now I denote it by W, right? So by construction, W acts from H tensor H prime into H tensor H prime. Now we have very nice relation between original map phi and this operator W. Namely, phi preserves hermiticity whenever W is Hermitian. Phi is positive whenever W is block positive, which means this property is satisfied, and eventually phi is completely positive whenever W is positive. And actually, relation like that between maps and operators was already studied by several people. Usually it is called channel state duality. It is often called Choi-Jamiukowski isomorphism. Okay, and now we have a concept of entanglement witness. An operator is called an entanglement witness if it is block positive but not positive. Right? In physics, this notion is very important because this operator, contrary to the original map phi, can be implemented in the experiment, because you know it can be interpreted as a quantum observable, because it's by construction it's Hermitian, right? Equivalently, it can be defined like that this is a Hermitian operator which enjoys this property for any separable state, but gives negative, but the trace is negative for some entangled state, right? And again, Horodecki's proves that a state is entangled if and only if you can find entanglement witness such that this property is satisfied. Again, with Gniewko, we discussed this topic extensively in this topical review. Okay, and now we have similar concept like decomposability. In decomposability, very, very interesting concept of optimality, bioptimality. I skip it, right? Now let me pass to another problem we discussed in recent years, namely quantum channels and quantum evolution. Okay, so given quantum system, the physical properties of a system are encoded into Hermitian operator, which we call Hamiltonian, system Hamiltonian. And given a Hamiltonian, there are two key problems. One of the problem is just to find the spectrum, right? Which is of great importance because knowing this eigenvalues, we know a lot about the properties of the system, molecule, atom, and whatever. And the second problem is to find the evolution, right? So suppose that at initial time 0, the system is in a state psi, and it evolves according to this equation, which we call Schrödinger equation. Very simple one, right? Linear equation. H is a Hamiltonian. This H bar is just a constant. We call it Planck constant. And trivially, this is a solution. So this is a unitary operator because H is Hermitian. So under Schrödinger equation, we have very simple unitary evolution of psi. And this simple picture can be immediately generalized. Well, this equation has almost 100 years. It was proposed by Schrödinger in 1926. And this problem can be immediately generalized to mixed states as well. So to simplify my analysis, I put H bar to 1. So this is the Schrödinger equation for pure state. This is the corresponding equation for mixed states. We call it von Neumann. And this is a solution, right? So again, you have unitary evolution of a density operator. And you immediately recognize that this unitary evolution, right? Well, you may consider a map, right? So this is the initial state. And lambda of t acting on rho gives you a state at time t, right? But you see, it's nothing but very special example of a completely positive and trace preserving map, because this is a very special example of this general scenario. I mean, cross representation with extra condition, which does guarantee that the map is trace preserving. So unitary evolution of a density operator provides just extremely simple example of much more general scenario, which corresponds to completely positive and trace preserving maps, I mean quantum channels. So the question is how to go beyond this very simple scenario. Okay, and for that we introduce a concept of quantum dynamical map. By that we mean a family of maps parameterized by time, such that initially this is identity, right? Initially, nothing happened to the state, but for any t non-negative, this map is completely positive and trace preserving. So we have a family of quantum channels, right? What's the origin of this more general maps? So this map is just one example, right? Standard Schrödinger evolution. This is a very special example of this much more general concept of quantum dynamical map. What's the origin? The origin is the following: that suppose that your system interacts with another one. Well, call it environment, rest of the world, whatsoever, right? In practice, no system is perfectly isolated from the rest of the world, right? It interacts. So now consider the Hamiltonian of the composite system. So we have a Hamiltonian of the original system, right? Hamiltonian of the environment, and the interaction Hamiltonian, right? This guy describes interaction between the system and the environment. Now suppose that initially the density operator of the composite system has a very simple form. Namely, it's a tensor product of the density operator of the system, tensor, density operator of the environment. Okay, so this is the initial system. Initial state of the composite system. This is the Hamiltonian of the composite system. So I apply exactly this simple scheme and consider the unitary evolution of the composite system. So it gives me this formula, right? So this is the evolution of the initial state, rho tensor rho e. Unitary evolution governed by the total Hamiltonian, right? Now, I perform partial trace, like, in this original Steinspring representation. So I just forget about environmental degrees of freedom, right? I am interested only in the degrees of freedom representing the system. So what comes out is a map, which is by construction, completely positive and trace preserving. Right, so you see, I have a unitary evolution of the composite system plus environment. However, after forgetting about degrees of freedom of environment, and for me it's very important because it may happen that the environment, it's a huge system, right? Look, I consider an atom interacting with the rest of the world. But the rest of the world is a huge system, right? It costs a lot to control the unitary evolution of the entire world. So I forget about the rest and I keep track only about the degrees of freedom of the system. However, the price is that the evolution of the system is no longer unitary. The system is open, right? Well, I open the system just forgetting about the degrees of freedom of the environment. By construction, this map is completely positive and trace preserving, but it's no longer unitary. So this scenario leads to exactly this kind of maps, right? Completely positive, trace preserving, but not necessarily unitary. The simplest example is provided by this famous semi-group of completely positive and trace preserving maps, which was fully characterized by Gorini, Kosakowski, Sudarshan, and Lindblad. Some of you for sure know this result, that the generator has this very, very elegant structure that, well, you recognize this piece, which you already seen in the von Neumann equation, right? So this piece is responsible for unitary evolution. right? But there is an extra piece. And this extra piece is responsible for going beyond unitary evolution. And this extra piece has, well, we call it dissipative part of the generator. And this dissipative part has this characteristic form. We have positive numbers, gamma k, these are called transition rates, and completely arbitrary set of operators, Lk. We call it quantum jumps, quantum noise, some people call it Lindblad operators. This is universal structure, right? So any generator of completely positive trace preserving semigroup has this form. I skip this. How to go beyond this very simple scenario. And recently we extensively studied this problem with Kasia Szydzińska, Szagnik, Chakraborty, Arpandas, and indeed Tagniewko and myself, also with a lot of collaborators. So basically, we are studying two approaches: time local one, which is based on the very similar equation, but now with time dependent generator, L of t, and another one which is based on the memory kernel approach, which means that the dynamical equation is represented by that kind of equation. Usually, this guy is interpreted, as kind of memory, because to compute the time derivative at time t, you need to know the whole history of the dynamics, starting from initial time up to current time t. So the basic problems which are related to this scenario are to find admissible time local generators, but by admissible I mean generators which gives rise to solutions which are physically legitimate. I mean completely positive and trace preserving. Actually, both problems are quite non-trivial. And another very much related problem is how to characterize quantum Markovianity beyond the simple semigroup scenario. Okay, I skip this and let me summarize some basic problems we are studying recently in our group. So positive maps in matrix algebras, especially non-decomposable maps. And this is very hard problem. We already provided several examples of such maps, but still the somehow general or more general construction is missing. So new constructions are needed, new ideas are required. Another important thing is relation between positive maps and quantum entanglement, especially the existence of PPT, positive partially transposed entangled states. Again, for this, we need new constructions because it's very hard to construct states which belong to this class. Another important problem is the construction of entanglement witnesses. We also currently we are working on other detection schemes, which somehow are slightly more general. They are related to other methods like correlation tensors and other scenario. I have no time to talk about this today. Then another important set of problems is related to evolution of open quantum systems. Properties of quantum dynamical maps. You remember family of quantum channels. And recently there is a big activity related to the notion of quantum Markovianity or non-Markovianity. a lot of papers in the literature because it turns out that the very notion of quantum Markovianity is very much context dependent. So there are several definitions on the market, and people are trying to find relations between them, and this is very, very hot topic. And working on that, we spent a lot of time trying to characterize generators, both time local and memory kernels. This is still an open problem. And recently, after Arpan Das joined us last November, we started to work on, did some work on quantum thermodynamics and relation to open quantum systems, but well, this is still in progress. But again, this is also very hot topic in recent years. Okay, that's all for the very first talk from our group. I hope that after summer vacation, we find more time to talk about more specific problems, and eventually find some common problems to work on. Thank you very much.
Okay, let us thank our speaker, and now it's time for questions. Any questions are welcomed. So I can see no questions.
Well, maybe I'll ask a naive question, because I've been looking at entanglement and things like that 40 years ago. And since that time, I haven't followed much. But I'm surprised that you are not referring to symmetry anywhere. When I looked at that, I thought the most important thing was that whenever we have a system that interacted, we have wave functions which are antisymmetric, and when we separate that and we want to have the tensor products, then they cannot be antisymmetric. And that, if you compute the distance between the states in this separated space, tensor space, and the original space, which was unified or antisymmetric, then there is always a big distance between such states. And I don't see any notion of symmetry in this matrix algebras that you've been talking about.
No, you are right. You're right that, well, in my talk, I did not consider this situation. I mean, because we are talking about undistinguishable particles, right? For that, we need extra symmetry. Either, right, the state has to be symmetric or antisymmetric. Well, I do not touch this problem. However, symmetry plays important role in our research, because several families of both positive maps and entangled states we constructed because we already imposed some extra symmetries, but symmetries of other type, right? Not related to distinguishability or not distinguishability of particles, but well, symmetry, basically symmetry of a class of operators. Well, of course, it's a good point.
But the entanglement doesn't seem to be possible without really having indistinguishability of elementary states, right, or particles.
No, it is. It's possible if they are well spatially separated. You can basically distinguish, right?
Yes, but can you get entanglement for particles that you can distinguish?
I think so.
Well, how come? I would like to see that. Okay. I thought that entanglement is really due to the fact that particles cannot be distinguished. Otherwise, I can't imagine how that could be possible. But
the very, very basic entangled pure state, let's say in the quantum teleportation protocol, is Bell state, is 0, 1 plus 1, 0. This is symmetric state,
Yes.
let's say, of a pair of photons, and this is entangled, yes?
Yes.
Entangled Bell state.
Yes, but that's because you have this combination of states, and that is because we cannot distinguish the photons.
Yes, yes. So
if we could distinguish particles, then there will be no need to have a combination. So I think actually the indistinguishability is the critical factor behind all the entanglement. But maybe I'm wrong. As I said, I haven't looked at these problems for a long time. So, well, I would like to see an example where you have, you know, distinguishability and yet you get the entanglement. And I just can't think about an example like that. But well. Okay, something to think about.
Okay. I can see that Tomek Piotrowski has raised his hand. Is it, am I right?
Yes, if I can ask one question. Thank you very much for this interesting talk. I tried to follow it, but I must say the notation, if one is not accustomed to it, is quite difficult. But I wondered about the mathematical properties of the object that has been described. And I wonder about convexity, because I just couldn't figure out how the convexity was used for to derive such a result that has been presented. I mean that the algebra and the operators, algebraic operators as trace, I can imagine, and the convexity, I just couldn't think how can that be useful. So if it can be just describe some more detail how this convexity can be exploited, then I would be grateful. Thank you very much.
No, the convexity is crucial. Following what the comment I would say critical, because somehow convexity using one of Banach's theorems, because of convexity we can well, basically what entanglement witness does, it separates convex subset of separable set from entangled states, right? So you see, for example, entanglement witness W, right? Knowing this witness, you can check that all states from this part are entangled, right? But this is possible only because the original set you are interested in is convex, right? So convexity in all this analysis is very important.
Yes, I would have to definitely read it in more detail, but
Sure.
this figure is convincing.
Sure.
Thank you very much. Thank you.
Thank you for your question.
Okay, so my comment yet is that quantum mechanics is just a non-commutative probability theory. So convexity is crucial because it represents statistical mixtures just of states. Yes, we have to be able to take convex combination of states. That's why theory is linear and the sets, interesting sets are convex.
Okay. I mean, without further reading, I can. But the Gniewko, what you said is yes, that's understandable to me. So.
Yeah, this was the starting point, right? So the construction of mixed states, right? So mixed states are convex combination of rank 1 projectors, right? So this is very basic. This is very basic object which is already convex, right?
Right.
So convexity is a key issue in all this analysis.
Yeah, because I know the convexity in Hilbert spaces from the point of view of optimization, where obviously convexity is absolutely.
Yes.
Right. So I wonder how it comes into equation here.
So it's not convexity in this underlying Hilbert space, but rather in Hilbert space of operators over H.
Yes. The slide is, I don't know, I just didn't understand it at first because perhaps the notation is unusual to me, so that's why.
I see. I hope that maybe, you know, next semester there would be a chance, you know, to present some more specific problem in much more details. So maybe things become more clear.
That would be great. It looks very interesting. Yes. So yeah, thank you very much for the answer.
Thank you.
Any other questions? Okay, if there are no other questions, so thank you, the speaker. Thank you to the people who asked interesting questions. And maybe that's all for today and for this semester with our seminars. Oh, thank you very much.
Okay, thank you.
Thank you. Bye.
Thank you. Bye, guys.
Bye.
Bye.
Thank you. Bye.
Bye-bye.
You. Bye.
Thank you. Goodbye.
Bye.
Okay.
No to kończymy.
Czyli co ty myślisz o tym? Lambda problem.
O, lambda problem. Wiesz, tam jest coś takiego, że zostaje poprawka liniowa i ta poprawka może być zarówno ujemna, jak i dodatnia. Więc tam nie można rozważać samej poprawki. Cieszyć się na przykład, że poprawka będzie zawsze ujemna. Nie, ona czasem jest dodatnia, czasem ujemna. Tylko tam jest tak dobrane, że jakbyś zobaczył, kiedy na przykład te stany są dokładnie, masz te wysycające jedynkę, wtedy poprawka jest zawsze ujemna. Natomiast dla innych, kiedy nie wysycają tej jedynki, może być dodatnia, tak? Ale to nie znaczy, że się nie zmieści pod tą jeszcze jedynką, pod tym progiem. Czyli samej poprawki tam nie może tak łatwo załatwić i no cóż, trzeba patrzeć dalej. Wiesz, tam już jest, tam są ten człon takich, suma tych iloczynów. Bez tych iloczynów zrobić, pokazać, że maksimum jest mniejsze od 1, to już jest nietrywialne. A z tymi iloczynami, bo jakby trzeba rozważać całość, dlatego że ta poprawka jest skorelowana z tym, ile mamy tam przestrzeni między tą sumą a jedynką. Jak jest przestrzeń, to poprawka może być dodatnia, jak tej przestrzeni nie ma, poprawka nie jest dodatnia. Czyli Czyli jak usunęliśmy ten problem, tak, z tą lambda kwadrat, to cały czas tam, no to się rozwiązanie tego skomplikowało. Chociaż trzeba myśleć, teraz patrzę nie przez to przez te kontrakcje ich wyznacznik, tylko przez obłożenie dowolnym separowalnym, no innymi rzeczami tam kombinuję.
Dobrze.
No się w każdym razie od naszego spotkania zmieniła postać rzeczy, bo to, co było przy lambdzie kwadrat, tak naprawdę teraz w jednym nawiasie z lambdą stoi, nie?
No tak, tak, tak.
Poczekaj, odbiorę, zobaczę, co tutaj jest. Okej. Jestem.
No dobra.
Nie, to mówię teraz jakby inną drogą, idę dlatego, że rozważyć ten wyznacznik, tak mniejszy od tam, że on jest większy równy 0, to jest no już bez tych wyrazów, tych iloczynów już to jest trudne do zrobienia. Teraz jak my podchodzimy, a teraz po prostu będę obkładał tymi wektorami i patrzył, co się w tym dzieje, nie? Korzystając z tej prostej formy, że to jest tam 1 minus 1, 1 minus 1. To coś tam daje nadzieję. Że to są dwa projektory bardzo do siebie podobne.
Okej.
A,
Czy jest jakaś szansa, że ktoś się przyłączy do nas? Chyba nie.
ale nie, wiesz, Tomek Piotrowski fajnie mówił na przykład, że on też jakieś tam, wiesz, convexity rozważa tam u siebie. Znaczy nawet nie chodzi, że się rozważa, ale czasami może po prostu nawet pokazać jakoś, wiesz, podrzucić jakiś temat, nie, że jest równoległa teoria, gdzieś tam jak na przykład w tej optymizacji on tam pracuje, tak, też w przestrzeniach Hilberta, też z jakimiś wypukłymi zbiorami, więc tam mogą być fajne wyniki na przykład, nie? Fajnie byłoby nawet go gdzieś tam poprosić, jak przejdą te pierwsza tura, że Tomek na przykład daje kolejny jakieś tam seminarium, nie? Zapamiętać go sobie, że go tam wytypować.
No dobra.
Dobra.
No na razie.
No na razie.